This is a review of class on May 15th, 2020. We really looked at three basic questions. Why are salts sometimes acidic or basic? We looked at some problems involving pH of salt solutions, and we spent a little time talking about what is in a solution during a neutralization reaction or a titration. All right, so I've written a couple things down. I started this and my camera malfunctioned, so I'll use some of the stuff I've written down previously. When we look at salt solutions, we know that salts come from the cation of a base and the anion of an acid. And so if the cation came from a strong base and the anion from a strong acid, then we know the resulting solution pH we'd expect to be 7. Now remember, there were three strong binary acids, HCl, HBr, HI. Other binary acids are weak. And then we also said that group 1 and group 2 bases are considered to be strong bases when they combine with hydroxides. So if you look at group 1, elements here except for hydrogen, elements here except for beryllium makes what are considered to be strong bases. Strong meaning that they separate completely in solution. If you recall the video that I showed you with the light bulb demonstration, the strong bases would make the light bulb light up a lot, and the weak bases would not have as many ions, and the light bulb would be dimmer. Same is true for the difference in strong and weak acids. All right, if I have a salt like potassium acetate, that's the next one down on my little sheet here, potassium acetate. The potassium came from a strong base, potassium hydroxide, because that's in the first column. And it came from a weak acid, which is acetic acid. The ionizing hydrogen would be, the acetic acid formula looks like this. It's HC2H3O2, and the ionizing hydrogen is that first one. So the difference is 2 minus 1, not strong enough to be, or not big enough to be a strong acid, because we said that strong acids have a difference between the oxygen and the hydrogen of greater than or equal to 2. All right, so something like H2SO4 would be strong, but H2SO3 would be weak, because the difference here is 2, strong, 3 minus 2, 1 is weak. All right, so since this came from a strong base and a weak acid, we'd expect the pH of the salt solution to be more than 7. If we have a salt of a weak base and a strong acid, now remember ammonium hydroxide, ammonium is not a group 1 or a group 2 element. It's actually a polyatomic ion. And iodine comes from one of the three strongs, so we got weak and strong, so we'd expect the solution to be acidic because it came from a strong acid but a weak base. So that'd be less than 7. Now you might be thinking, what if they're both weak? If they're both weak, then you have to go look up the magnitude of the ionization constants, but we're not going to get into that in this class. So if I have a solution of acetic acid, we're going to spend a little time now talking about why is it that these pHs are what they are. What I've shown you is a way to tell what they are, but we haven't talked about why. So I want to talk about why. All right, so my camera is malfunctioning again, so just one moment here. Let's reload the page. All right, here we go. So I had written a little bit more, which you couldn't see. So this is the equation for acetic acid in water, reacting with water. Remember, this is one of those acids that made a really dim light bulb. So that means that in the solution, you've got a lot of these things over here. There's just a lot of acid, but there's a tiny amount of these things. So a tiny amount, we'll put that in quotes because it's not too technical a term. But you might think if I have 1,000 of these, I might have 999 that didn't react and only one that turned into the hydronium and the acetate. All right, so there's a whole lot of this. That would mean then that this ion, this C2H3O2, it is very much attached to this hydrogen. It does not want to lose a hydrogen. That's why it doesn't, because you have just a tiny amount of these hydrogens that come off and react with water to make this ion. So since it wants a hydrogen so bad, consider what would happen if I put a solution of potassium acetate in water. Well, you should know that potassium acetate is a soluble salt. Let me just show you that real quick. So going over to chemical equations, where I have a little help sheet stashed away. So this is what I always call the equation help sheet. Remember these solubility rules? It says, first one, all common salts of alkali metal and the ammonium ions are soluble. So if you consider what are alkali metals, that's this first column right here. And potassium's right there. So that means potassium makes soluble salts. Well, if that's the case, then potassium acetate will not stay together in solution. It'll come apart like this. And this ion right here, it's an ion from this acid, and this acid does not want to lose protons. So if this ion is floating around the solution, it's thinking, I'd like to have a proton back. Well, you've got this acetate floating around. It is, of course, you'd write an AQ up here. It's dissolved in water. This is solid before it dissolved. So if it's floating around in water and it's looking for a hydrogen, did you notice that water has a hydrogen? And so one of the hydrogens will be pulled off a little. It doesn't happen to every water molecule, but a few molecules of water will actually lose a hydrogen to that acetate. So we get a new equilibrium that looks like this. And OH ions are left behind. Now you'll remember that OH ions are the ions that are characteristic of bases. And so that makes a solution become basic, and that's why the pH is greater than 7 up there. All right, so pHs of solutions with strong base cations and weak acid anions. The anion from the weak acid didn't want to lose its proton, so the anion pulls a proton off of the water and becomes an unionized acid molecule. But when the water loses its proton, OH is left behind. The same thing happens for acids. I'll go through that one quicker. So if I have ammonium ion, and I add water to it, what happens is the ammonium can't gain a proton, it has to lose one. So it's going to lose it back to this water, because ammonium didn't want to gain it in the first place, because ammonium comes from a weak base. So you're going to end up with NH3, and then water has gained a proton, so now it's H3O with a positive charge. So that is why that makes the pH of the salt solution acidic. It's going to be less than 7. All right, so there's why the pHs of salt solutions may not be 7. Now, if the ion's from a strong acid and a strong base, both of them wanted to ionize, and so there's no attraction for the protons from water, or no desire to give a proton to water. All right, the next thing I wanted to look at today was problems involving pH of salt solutions, and I'm going to show you a quick relationship. I'll use the equations that I already have. Well, I'll rewrite them. Okay, I'm going to stop this video here, and I'm going to work on the camera for a minute, and we'll start again.